The Strip. Two words that conjure immediate images: cascading lights, impossible architecture, fountains that erupt on schedule, replicas of global landmarks compressed into a single boulevard. It looks effortless now. A tourist arrives, checks into a tower with 3,000 rooms, rides elevators programmed by algorithms, walks through climate-controlled atriums where the temperature never shifts. The experience feels inevitable, as if Las Vegas simply materialized fully formed in the Mojave. But every volt of electricity, every cubic yard of concrete, every gallon of water pumped uphill from Lake Mead represents a calculated answer to a specific engineering problem. This is not the story of casinos or entertainers. This is the story of how empty desert became the most densely packed concentration of artificial infrastructure in North America, and why building it required solving problems that didn't exist anywhere else. The paradox starts with location. Las Vegas sits in a valley surrounded by mountains, where summer temperatures routinely exceed 115 degrees Fahrenheit and annual rainfall averages 4 inches. There is no natural harbor, no navigable river, no timber, no coal deposits. The nearest major city is Los Angeles, 270 miles west across a mountain range, and the most unforgiving stretch of the Mojave. In 1905, when the San Pedro, Los Angeles and Salt Lake Railroad auctioned off lots in what would become downtown Las Vegas, the settlement consisted of a train depot, a few tents, and access to underground springs that made the valley marginally less hostile than the surrounding wasteland. The railroad needed a midpoint maintenance stop. That was the extent of the plan. For 2 decades, Las Vegas remained exactly that, a railroad town with a permanent population below 5,000, serving as a watering hole for steam locomotives. Then in 1928, Congress authorized construction of Hoover Dam, 40 miles southeast. The official reason was flood control and irrigation for California's Imperial Valley. The practical result was the largest civil engineering project attempted in the United States to that point, requiring a workforce that would peak above 5,000 men working in 3 shifts around the clock. Those men needed housing, food, equipment, and entertainment during off hours. Las Vegas, despite having almost no infrastructure, was the only incorporated municipality within reasonable distance. The dam transformed the local economy overnight, but it also created the first technical challenge that would define the city's development: how to support a population far exceeding the capacity of natural water sources. The solution involved drilling deeper wells and constructing a pipeline network that pulled groundwater from multiple aquifers beneath the valley. By 1931, the city had installed its first centralized water treatment facility, a modest concrete building on East Bonanza Road capable of processing 2 million gallons per day. That figure would need to increase by an order of magnitude within 15 years. The dam workers brought cash, and cash attracted businesses that had nothing to do with construction. In 1931, Nevada legalized gambling statewide, and Las Vegas issued its first casino licenses. The El Cortez, the Apache Hotel, the Northern Club. These establishments operated on a scale appropriate to the town's size, with player capacities measured in dozens, not thousands. But they established a pattern. Las Vegas could attract temporary populations willing to spend money, provided there was infrastructure to support them. Hoover Dam, as it was later renamed, was completed in 1936, 2 years ahead of schedule. The workforce dispersed. The city's population dropped. But the dam itself became the city's most important asset, not because of the reservoir it created, but because of the hydroelectric power it generated. 6 turbines began operation in 1937, each capable of producing 82,500 kilowatts. The dam's electrical output fed the newly constructed transmission lines running west to Los Angeles and north to Boulder City. Las Vegas tapped into those lines. For the first time, the city had access to cheap, reliable electricity in quantities far exceeding local demand. That surplus would make everything that followed technically possible. The next phase required a different kind of infrastructure: Highway 91. Before 1938, the road connecting Las Vegas to Los Angeles was unpaved for long stretches, impassable during flash floods, and lacked reliable fuel stations. The federal government, responding to military logistics concerns as war loomed in Europe, funded a paving project that transformed the route into a 2-lane asphalt highway capable of handling heavy truck traffic year-round. Travel time from Los Angeles dropped from 12 hours to 6. The highway didn't just connect two cities, it created a corridor through which materials, labor, and capital could move in both directions. Los Angeles had wealth and workers. Las Vegas had electricity and legalized gambling. The highway made exchange possible. By 1940, Las Vegas had 8,000 residents and a downtown gambling district operating at modest scale. Then came December 1941 and the country's entry into World War II. The federal government constructed a military airfield northeast of the city, later designated Nellis Air Force Base, and established a magnesium processing plant in nearby Henderson to support aircraft production. Both facilities required workers, and workers required housing, food distribution networks, and expanded electrical capacity. The population doubled in 3 years. The infrastructure that had been adequate for a railroad town was now operating beyond design limits. Water became the immediate crisis. The aquifer wells drilled in the 1930s could not sustain demand. Engineers surveyed the valley and identified a solution that seemed absurd: pump water uphill from Lake Mead. The reservoir created by Hoover Dam, across 25 miles of desert and over a mountain ridge rising 650 feet above the valley floor. The project required construction of a dedicated pumping station at the lake, installation of a 30-inch diameter pipeline capable of withstanding internal pressures exceeding 300 pounds per square inch, and a secondary pumping facility at the valley's edge to push water the final distance into the municipal system. The first phase was completed in 1942. Capacity: 10 million gallons per day. The pipeline route followed existing railroad and highway corridors to minimize new excavation, but crews still had to blast through sections of solid rock and install expansion joints to accommodate thermal stress. Desert temperatures could swing 70 degrees between midnight and noon. Steel expands and contracts. Joints that couldn't flex would rupture. The war ended. The airfield and magnesium plant didn't. Nellis became permanent, housing over 10,000 personnel. The city now had a stable military presence, generating consistent demand for off-base services. That stability attracted a different category of investor. In 1946, construction began on a property that would redefine what a Las Vegas casino could be. The Flamingo, located on Highway 91 south of the existing city center, was not designed as a downtown gambling hall. It was conceived as a self-contained resort. Casino, hotel, restaurant, showroom, swimming pool, and retail space integrated into a single property occupying 40 acres. The project's financial backing came from sources that operated outside conventional banking channels, but the construction contracts went to licensed firms employing union labor. Concrete, steel, glass, and copper wiring follow the same physical laws, regardless of who signs the checks. The Flamingo's design presented engineering challenges that had no precedent in Nevada. The hotel tower required a foundation capable of supporting a 4-story structure on soil with minimal load-bearing capacity. Contractors drove concrete pilings 30 feet into the ground, creating a grid of reinforced columns that distributed the building's weight across a wider subsurface area. The casino floor, by contrast, couldn't have support columns interrupting sightlines and player movement. The solution involved installing steel trusses across the ceiling cavity, spanning distances up to 60 feet without intermediate supports. Each truss weighed several tons and had to be lifted into place by crane, then welded to anchor points embedded in the perimeter walls. Climate control was the more complex problem. A casino operates 24 hours, generates heat from thousands of light bulbs and human bodies, and cannot have windows that open. Refrigeration systems in 1946 were designed for small commercial spaces, not 40,000 square foot interiors in a desert climate. The Flamingo's mechanical engineers installed a central chiller plant with ammonia-based compressors, the same technology used in industrial cold storage facilities. Chilled water circulated through a network of pipes to air handling units distributed across the building. Those units blew cooled air into the occupied spaces through ceiling-mounted diffusers. Return air vents pulled warm air back to the handlers for recooling. The system consumed enormous amounts of electricity. The Flamingo's peak electrical load exceeded 2,500 kilowatts, roughly equivalent to the total power consumption of downtown Las Vegas a decade earlier. Without Hoover Dam's surplus capacity, the building would not have been technically feasible. The property opened in December 1946, closed 2 weeks later for refinancing and completion of unfinished interiors, then reopened in March 1947. Despite initial losses, the Flamingo demonstrated a functional model, a large-scale resort on the highway corridor, offering amenities that couldn't fit within downtown's limited real estate. Other investors noticed. Within 3 years, 4 additional properties opened on the same stretch of highway: the Thunderbird, the Desert Inn, the El Rancho, the Last Frontier. Each required its own well or pipeline connection, its own electrical substation, its own septic system. The city's municipal infrastructure couldn't extend that far south. Developers had to build their own utilities. This created redundancy and inefficiency, but it also allowed construction to proceed without waiting for municipal approval or budget allocation. A developer who could finance a hotel could finance a water tower. By 1950, the highway corridor had its own parallel infrastructure network, privately owned and maintained. The Strip was emerging as an autonomous zone, geographically separate from the city, operating under county rather than municipal jurisdiction, and solving its own technical problems through capital expenditure. The 1950s brought scale, not incremental growth but geometric multiplication of every variable: room count, floor area, electrical demand, water consumption, structural complexity. The Sahara opened in 1952 with 240 rooms. The Sands followed in 1953 with 200 rooms, but a showroom designed for 600 guests. The Riviera arrived in 1955 with 9 stories, making it the tallest building in Nevada. Each property competed on size and spectacle, and size required solving problems that didn't exist at smaller scales. Foundations became critical. Desert soil in the Las Vegas Valley consists primarily of caliche, a sedimentary layer formed by mineral deposits that can resemble concrete when dry, but loses cohesion when saturated. Engineers couldn't simply pour a slab and build upward. For the Riviera's tower, contractors excavated to a depth of 15 feet, removing unstable surface material until they reached competent bearing strata. They then poured a reinforced concrete mat foundation, a single monolithic slab 4 feet thick, covering the entire building footprint. Steel rebar was laid in a grid pattern with bars spaced 12 inches apart in both directions. The slab weighed over 4,000 tons before construction of the tower even began. Concrete trucks arrived in continuous rotation for 72 hours during the pour, because stopping would create cold joints where cured and uncured concrete meet, creating weak points vulnerable to cracking under load. Vertical construction introduced new requirements. A 9-story building needs elevators, and elevators need shafts, and shafts need fireproofing. Nevada had minimal building codes in 1955. Developers could reference standards from other states, but enforcement was inconsistent. The Riviera's elevator shafts were constructed from poured concrete rather than the steel frame and drywall assemblies common in commercial buildings elsewhere. Concrete provided both structural support and fire resistance, but it required careful sequencing. Workers built wooden formwork to define the shaft's interior dimensions, poured concrete around it in sections, waited for each section to cure, then raised the formwork and repeated the process. Each floor took approximately a week. The tower's construction schedule stretched to 18 months, triple the time needed for earlier low-rise properties. Air conditioning capacity scaled with building volume, not linearly. A 9-story tower contains roughly 3 times the interior space of a 3-story building, but it requires more than 3 times the cooling capacity because heat rises, upper floors absorb solar radiation from all sides, and guest rooms generate heat from occupants, televisions, and lighting regardless of outdoor temperature. The Riviera's mechanical plant occupied an entire basement level, housing compressors, chillers, pumps, and a cooling tower mounted on the roof. Cooling towers work by evaporation. Warm water from the chiller system is sprayed into the air, where a portion evaporates, carrying away heat and lowering the temperature of the remaining water, which recirculates back through the system. In desert air with humidity below 10%, evaporation is extremely efficient, but it consumes water. The Riviera's cooling tower evaporated approximately 50,000 gallons per day during summer operation. That water had to come from somewhere. The Strip's private water infrastructure was reaching its limits. By 1955, properties were drilling wells to depths exceeding 800 feet, chasing aquifer levels that had dropped due to cumulative extraction. The alternative was connecting to the municipal pipeline from Lake Mead, but that required negotiations with the Las Vegas Valley Water District, formed in 1948 to manage regional water resources. The district agreed to extend service south along the highway corridor, but developers had to fund the extension themselves. In 1956, a consortium of Strip properties financed construction of a 24-inch main line running from the city limits to the Sahara, a distance of approximately 4 miles. The pipeline cost $800,000, split among participating properties based on projected water usage. Electricity followed the same pattern. Nevada Power Company, the regional utility, upgraded its transmission infrastructure to handle Strip demand, but casinos had to pay for dedicated substations and transformer vaults on their own property. The Dunes, which opened in 1955, installed 3 transformers rated at 1,500 kilovolt amperes each, stepping down high-voltage power from the utility lines to usable levels for building systems. Those transformers were housed in a concrete vault with ventilation louvers to dissipate heat. Transformer failure was catastrophic. A property that lost power lost revenue at a rate of thousands of dollars per hour. Redundancy became standard. Multiple transformers, backup generators, automatic transfer switches that could detect power loss and reroute electrical supply within seconds. The construction boom required materials in quantities that exceeded local supply. Concrete aggregate was mined from pits north of the city and transported by truck. Structural steel came by rail from mills in California and Utah. Glass, particularly the large plate sections used for casino storefronts and hotel facades, was manufactured in Los Angeles and shipped in custom crates designed to prevent breakage during transport. Skilled labor was imported. Electricians, pipe fitters, ironworkers, and crane operators came from California, working on contracts that included housing allowances because Las Vegas didn't have sufficient residential capacity for temporary construction workers. Some contractors built their own dormitories. The 1960s saw consolidation and corporate ownership replacing individual investors. Howard Hughes arrived in 1966 and purchased the Desert Inn, the Sands, the Frontier, and the Landmark within 2 years. His holdings were managed through Summa Corporation, which operated under standard corporate accounting and regulatory oversight. This shift made large-scale financing accessible through conventional banks and insurance companies that had previously avoided Nevada gaming investments. The impact on construction was immediate. Projects could now secure loans backed by institutional lenders, which demanded detailed engineering specifications, bonding requirements, and compliance with evolving building codes. Caesar's Palace, which opened in 1966, represented this new era. The property covered 34 acres and cost $24 million, financed through a combination of private equity and bank loans. The design incorporated architectural elements referencing ancient Rome, but the engineering was entirely contemporary. The main casino building used post-tensioned concrete construction, a technique where steel cables are threaded through hollow channels in poured concrete, then tensioned after the concrete cures. This creates compression that counteracts tensile stresses, allowing longer unsupported spans and thinner structural members. The casino floor achieved column spacing of 90 feet, creating sightlines uninterrupted across the entire gaming area. The property's signature feature was an outdoor fountain complex with computerized controls. Water jets could shoot 80 feet into the air in choreographed sequences timed to lighting effects. The system required underground pump vaults, filtration equipment, and a dedicated electrical supply isolated from the main building to prevent hydraulic surges from affecting gaming equipment. The fountain recirculated water, losing only what evaporated, but the initial fill required 120,000 gallons. Maintenance crews had to drain and clean the system quarterly to prevent algae growth and mineral buildup. By 1970, the Strip had 20 major properties, and the cumulative infrastructure demands were straining regional capacity. The Las Vegas Valley Water District expanded the Lake Mead pipeline to a 48-inch diameter main, capable of delivering 90 million gallons per day. Nevada Power Company constructed a new generating station at the Reed Gardner facility north of Las Vegas, adding 250 megawatts of coal-fired capacity to the grid. The Strip's growth was no longer constrained by utility availability, but by land and capital. The next transformation came in the 1990s, with the introduction of mega resorts that functioned as destination complexes rather than standalone hotels. The Mirage, opened in 1989, occupied 102 acres and cost $630 million. It included 3,044 rooms, a showroom for 1,500 guests, a habitat for white tigers, and an artificial volcano that erupted on schedule using natural gas jets and theatrical fog. The construction required excavation of a lake, installation of a 1-million-gallon aquarium behind the casino registration desk, and structural reinforcement to support the weight of water features distributed across multiple floors. MGM Grand followed in 1993 with 5,005 rooms, the largest hotel in the world at the time. The building occupied 45 acres and rose 30 stories. Its foundation consisted of a reinforced concrete mat 11 feet thick, supported by 1,200 caissons drilled 60 feet into bedrock. The casino floor covered 171,000 square feet on a single level. Air handling for that space required 24 rooftop units, each weighing 12 tons and processing 30,000 cubic feet of air per minute. The property's electrical demand peaked at 18 megawatts, equivalent to a small city. Bellagio, opened in 1998, introduced technical challenges related to its 8-acre artificial lake and choreographed fountain system. Engineers designed a concrete lake bed with a synthetic liner to prevent seepage into the surrounding soil. The fountain system used 1,200 individual nozzles controlled by computer, capable of shooting water 460 feet into the air. Pumps delivered water at rates exceeding 80,000 gallons per minute during full displays. The choreography software synchronized water jets, lighting and music with precision measured in milliseconds. A single performance consumed electrical power equivalent to operating 600 average American homes simultaneously, but only for minutes at a time. The Venetian, completed in 1999, replicated sections of Venice, including functional canals navigated by gondolas. The canals required waterproofing systems that could withstand constant submersion, filtration to maintain water clarity, and climate control to prevent evaporation from raising interior humidity levels. The property also introduced all-suite room configurations, with the smallest unit measuring 650 square feet, double the industry standard. This required more complex plumbing and HVAC distribution, with separate climate zones for sleeping and living areas within each suite. Modern Las Vegas consumes 219 billion gallons of water annually, 90% of which comes from Lake Mead through pipelines that now include a third intake tunnel completed in 2015, designed to draw water from depths below the reservoir's declining surface level. The city uses 5,600 megawatts of electricity at peak summer demand, supplied by a grid connecting hydroelectric, natural gas, solar, and imported power from regional sources. The infrastructure that supports 40 million annual visitors was not planned. It accumulated through incremental responses to immediate technical problems, each solution enabling the next phase of expansion. Empty Desert became Neon Empire because engineers found ways to move water uphill, generate electricity in quantities that didn't exist locally, and cool buildings in temperatures that should have made large-scale human occupation impossible. The lights stay on because systems built decades apart still function in coordination, a network assembled piece by piece, now operating as a single continuous machine.